So this will pick up where the last video ended, where we will use the Excel functions, the norm.dist and norm.inverse functions, to start answering some questions about using those two functions to estimate probabilities and find values that are associated with probabilities. So I'm going to do this only, well, I'll do it for both. It's easy enough to do for both. But I'm going to go ahead and delete this right here from Microsoft. I'm going to clean some things up a little bit just to show you how to make a pivot table look a little bit nicer and not lose a lot of information. So I'm going to go ahead and delete all of this over here for Microsoft right now. So if you look at these bins, they're not formatted very well. They don't look very nice. So blank is showing up because we just highlighted the entire column and notice there are no values associated with blank. And it's going to pick up all these cells down here that don't have anything in them. So I want to clean this up just a little bit. So if we look at the Tesla returns, they go from negative 36% up to positive 75%, just over positive 75%. So when we go in here and we try to group this, instead of that negative 0.36, that really long value right there, I'm just going to go to negative 0.4, which would be the same as negative 40%, and I'm going to go up to 0.8%. And when you do that, it's going to make the bins a little bit nicer to look at. Notice we didn't lose a lot of information here. And it's only going up to that maximum value anyway. So even though I put a higher upper bound, it didn't matter because there's nothing up there. To get rid of this negative 0.04 or blank, or less than negative 0.04 or blank, we can come up here and just turn that one off if you want to. And that'll clean it up just a little bit more. Where things get a little weird is when you're really close to 0. So what this is actually measuring is negative 2.5% to 0, because this value says move that decimal place to the left 17 places. It's just a formatting thing in Excel that looks a little bit weird. So this is a little bit easier to work with. The bins are a little bit nicer than they were when you just use the raw values. So I'm going to clean it up just a little bit more because I'm not worried about the precision on the plot at this point. I just want to do some things that might be a little easier to compare to the probabilities that we estimate in just a few minutes. So I'm going to change this, instead of 2.5%, I'm going to change that to 5% right here, so that our table's a little bit more condensed. Right. So I'm going to move this over here, and I'm also going to just cut all of this. I'm going to do a Command X there and just paste that over here. Okay. Just to make it look a little bit nicer. Because what I want to do is I want to estimate some probabilities where, let me actually get those blanks off of there again. We want to estimate probabilities and then compare them to what we actually observed. Because the probabilities that we estimate are going to be assuming the normal distribution is correct, and then we can compare that to what we're actually observing right here. So the one thing I want to do first, just to convert these frequencies to probabilities, is if you come over here and just make a column called, in this case, prob for probability, I want to know the probability of observing a return within each range. And to do that, we take the number of returns that fall within a certain range and we divide it by the overall number of returns. So here, this is going to be equal to N18, so the value in that cell. You have to type it instead of clicking in the table because it looks a little weird if you click in the table. Then I want to divide that by 119 because that's how many returns we actually have. 0.008. And I'm going to drag this down right here. So I'm going to clean that up just a little bit by removing some of those decimals. decimal places. Right. So these are now probabilities. So we would say, I'm going to we have a few more, uh, that about 12.61% of returns are between 0 and 5%. So those 15 returns that are within 0 to 5% represent about 12.61% of all returns. So we see that these are really rare. These are really rare. Most of the actions happening somewhere in this range right here. So most of the returns are going to be between negative 15% and positive 15%. If you look at this, if you highlight that, notice down here at the bottom, sum is 1. That represents 100% of the data. So 100% of the time, we will observe a return between negative 40% and 75% in this sample. So we want to estimate a few probabilities. So the first thing we want to do, I'm going to come over here to the right, and let's find the probability that the return is less than 0. And what we're going to do is estimate this probability assuming this mean and this standard deviation are correct and the returns follow a normal distribution. And if under those two assumptions, what would we expect to see right here on for this probability? Right. So to do this, we're going to use the norm.dist function. So let me back up just a second here. So if you remember from the lecture, there are a couple things we can do with this normal distribution. So we can find the probability that x is less than some value, greater than some value, or between some values. So this is what we're going to do first. Well, we're going to set x not equal to 0, and we're going to assume mu is the sample mean is mu, and the sample standard deviation is also, and sigma is what we observed in the sample standard deviation. So to find the probability that the return is less than 0, we're going to do equals norm.dist. X is 0. Just get in the habit of putting the percent sign on there. So we're going to be less than 0%, so less than 0, when the mean is H2 and the standard deviation is H4, and we always put true. So anytime you're working with a norm.dist function, always use the true option there, so it returns a cumulative probability. And this is going to tell us the probability of observing a value that's less than 0 when the mean is 4.34% and the standard deviation is 18.03%. If we hit enter, we get 0.40. So the probability of observing a return that's less than 0 would be 0.4, assuming this is the correct mean and this is the correct standard deviation. For Microsoft, if we just drag this over, we're going to get 0.35. So notice that the mean for Tesla is greater than the mean for Microsoft, but the probability of observing a negative return is higher for Tesla than it is for Microsoft. That's because the standard deviation is so much larger. And when that standard deviation is so much larger, we get returns that we're more likely to observe values further from the mean. So even though Tesla has a higher return than Microsoft, the probability of observing a negative return is higher for Tesla than it is for Microsoft because of that higher standard deviation. Right. Again, I'm going to format these to, I'm just going to come down here and format a bunch of cells to 2 decimal places to make our life a little bit easier. Right. So it's higher for Tesla than it is for Microsoft. So what we just did there is we found the area under the curve to the left of 0. So we're assuming that x naught is 0 in this case. The next thing we can do is find the probability that the return is greater than some value. So what's the probability that the return, let's just say for example, is greater than 5%? So if we use the norm.dist function and we enter 5%, it's going to give us the probability that the area is the area under the curve to the left of 5%. So what we're doing is we're setting this x naught equal to 5% and entering the values from u and sigma from our sample, and we're going to find that area under the curve to the right of 5%. But notice we have to do 1 minus the norm.dist. Because norm.dist is going to give us this area to the left, we have to subtract that from 1 to get the area under the curve to the right. So this is going to be equal to 1 minus a norm.dist, 5%, when the mean is h2 and the standard deviation is h4, comma, true. So 0.49 for Tesla and 0.33 for Microsoft. So the probability that we observe a return greater than 5% is higher for Tesla than it is for Microsoft. So we would assume if this is the true mean and this is the true standard, if these two values are the true means and these two values are the true standard deviations, and it's truly normally distributed, we would assume returns greater than 5% more often for Tesla than we do for Microsoft. So if you're looking at a table right here, we're going to find 5%, which is right here, and we're going to go greater than that. So we're going to look at all of these probabilities right here, because that would be the probability that we're greater than 5%. And what we're actually observing in the sample is down here, you can barely see it, is 0.41. What we're getting is 0.49. So not too far off, but not exactly the same. So for this one, the true value, if it was truly normal, would be 0.4. If we look at this right here, we look at all these probabilities less than 0, we get 0.46. So it actually occurs more often than we assume it would if it were truly normally distributed. And that's kurtosis risk. I mean, we're observing extreme values more often than we would if we assumed a normal distribution. The next thing we can do is find the probability that the return is between two particular values. So what we can do, let's just pick some from the table here. Let's find the probability that the return is between 10 and 15%. So in our sample, we observe a return between 10 and 15% for Tesla about 9.24% of the time. So let's find the probability that the return is between 10% and 15%. So what's the probability that the return is between 10 and 15%? If it's truly normal, we would get norm.dist. We always, actually, let's go back just a second. This is what we're looking for right here. We're going to set this to 10%, this to 15%, and we're going to find that area in between. And we have to use the norm.dist function twice to get that area in the middle. So this is the first one's going to be a norm.dist on the 15% when the mean is h2 and the standard deviation is h4. Okay, so that's going to give us the probability that we're less than 15%, but we need to subtract that area to the left of 10% since we don't want that in the calculation. So we're going to do another norm.dist on the 10% when the mean is h2 and the standard deviation is h4. And we would expect that to occur with about probability 0.1 for Tesla and about 0.09 for Microsoft. And if we come down here for Tesla and we look between 0.1 and 0.15, in our sample we observe returns between 10 and 15% about 9.24% of the time. this says we should observe it about 10% of the time. So notice the numbers are different, and that's because these returns are not truly normally distributed. We're just making an assumption. And these are the probabilities we would observe if they were normally distributed with these means and these standard deviations. So what we observe in the sample isn't necessarily what we observe in theory if the normal distribution was the true underlying distribution. Right? So that's the norm.dist. That's how we find the values that correspond to those. That's how we find the probabilities that correspond to those x values. So I give you the x, the return, and I ask for the probability that it's associated with that. The other type of problem that we can solve with the normal distribution is how to find x values that are associated with probabilities. So, for example, I want to know the Tesla return that represents the bottom 10% or the Tesla return that represents the top 10%. So to do that, we're using the norm.inverse function. So the norm.inverse function is right here. So I'm going to give you a probability or an area, and I want to know the x value that satisfies that probability statement. So if I say, give me the Tesla return such that only 10% of returns are smaller than that, I'm looking for this x value, and that area would be 0.1. Or if I ask you, what's the Tesla return such that only 10% of returns are greater than that number, this area to the right would be 0.1. The area to the left of that would be 0.9, and I'm asking for this value right here. So we can do that using the norm.inverse function. And the way I'm going to write this is I want to find, let me just be to be consistent with the notes. So I want to know the probability of x being less than return equals, I'm gonna call this 0.1. Another way of writing that, I don't like that notation. I'm just gonna call it return for the bottom 10%. So when you see it written like this, what I'm looking for here is the return such that the probability of being less than that is 0.1. So to do this using the norm.inverse function, so we're going to do a norm.inverse, and this is where we put 10% for the probability. Technically, we're supposed to put 0.1, but if you do 10%, it will be formatted the way it's supposed to be formatted. It'll be formatted correctly. So 10%, the mean is H2, the standard deviation is H4. And we can format this as a percent because it should be in the same units as the mean. Let's drag this over for Microsoft. So this tells us that we would expect to observe a return that's less than negative 18.77% approximately 10% of the time for Tesla. And for Microsoft, we would expect to observe returns less than negative 5.6% approximately 10% of the time. So if you're thinking about it visually here, this x naught for Tesla would be negative 18.77, and the area that you see shaded right there would be 0.1. And for Microsoft, that area would still be 0.1, but that would correspond to an x value that's negative 5.60, which is what we would expect since Microsoft has a much smaller standard deviation. We would expect those extreme negative values, to occur with a lower probability. We can also find the return that represents the top 10%. So if we want to know what is the return that satisfies the top 10%, another way of saying that is we want the return such that we observe something smaller than that 90% of the time. So if we observe something larger than that 10% of the time, we would observe something smaller than that. Yeah, make sure I said that correctly. If we observe something larger than that 10% of the time, we would expect to observe something smaller than that 90% of the time. So this will be the return for top 10%. Again, you can set these percentiles to anything you want. I'm just doing 10% to be consistent across the two problems. Where you have to be careful here is when you enter probabilities in Excel, it assumes to the left. So if we want this shaded region to the right to be 0.1, the area to the left of that is 0.9, and that's what we actually have to enter in Excel. So notice this is 1 minus alpha, where alpha is the probability. So if we want to find the value that represents the top 10%, we have to do norm.inverse 1 minus 10% with a mean of H2, standard deviation of H4. And this will give us the return such that the probability of being greater than that is 0.1, less than that is 0.9. But those are our equivalent statements. So if we drag this over, format that as a percent, because these should always be in the same units as the mean, which is a percent. Give ourselves some more decimal places. We expect to observe a return for Tesla, if it's truly normal, we would expect to observe a return greater than 27.46% about 10% of the time, if it's truly normal. And we would expect to observe a return of that's greater than 10.21% about 10% of the time for Microsoft. Again, that larger standard deviation says we're more likely to observe those extreme values for Tesla than we are Microsoft. It has a higher mean, but it also has a higher standard deviation, which says values far from the mean are more likely to occur for Tesla than they are for Microsoft. So that's how we use the norm.dist and norm.inverse functions. Students always ask, how do I know which one to use? If I give you returns and ask for probabilities, it's norm.dist. If I give you probabilities or percentiles and I ask you to find the return, that's a norm.inverse problem. And again, all of this over here was just to show you that this is what we would expect if it's truly normal with these means and these standard deviations. This is what we actually observe in the sample, and those two things are different. So in the next video, I'll show you a few more things just about normal distribution and how the shape of the distribution changes as we change the mean and standard deviation.